All right, let's take a look at this example to find the singularity function or discontinuity function for this beam. And I see from this beam I have a 3 kilonewtons per meter over half of the span. Um, yeah, let's get at it. The first step we said in this process is to use statics to solve for your reactions. And there it is. I jumped ahead because I figured the static should be review. I did some of the moments about A. I found a reaction at By, or at B to be 3.75 kilonewtons, and at A, 11.25 kilonewtons. So we said step 2 was develop a function, develop our singularity function. So like I said in the previous video, I would typically start with the moment function, but in this one I'm going to work all the way through and look at my loading function. I just think it'll be good to go through the process once, and then the second example I'll do it the way I would normally do it, just going straight to the moment function. So looking at the loading function, my load is a W, or an omega, is a function of x. And to develop this equation, what I'm going to do is I'm going to look at each one of these forces, distributed loads, and I'm going to use our table that we had last time. So the first thing I'm going to look at is that 11.25 kilonewtons right there, and that's a point load. So I come up to my table and I see that's case number 2, point load, straight up. I'm doing the loading function W, so this is the equation I'm going to add for that. My load due to that point load, or my loading function, is P x minus A to the negative 1. So putting it in here, P is the magnitude of the force. Our force is 11.25. It's our reaction. And then I have my brackets, x minus A. Now A is the distance from the left-hand side. In this case, it's 0. And that is to the negative 1 power. The next one we need to look at is this distributed load. So we go back to the table and say, well, it's case number 3, where we have a distributed load. Now be careful of the signs. Our distributed load is actually pointing down, not up. So I am going to be using this function, but I'm going to have a negative in there. That W0 will be negative 3 for our case, and it's also starting at A equals 0, right on the edge of the beam. So like I said, I'm going to have minus, because it's pointing down, 3, that's at 3 kilonewtons per meter. My singularity function or discontinuity function, x minus A, in this case A is 0. This is to the power of 0 according to that table. So if I keep moving along, here's the issue, is that this basically turned on the distributed load. Now the issue is we don't want our distributed load over the entire beam. We want to turn it off right at this x equals 5. So the trick here is that in essence we're going to add the opposite for the second half of the beam. So what that's really saying is if I were to look at this beam, and when I turned on that distributed load, I'll draw it in red, it did it throughout the entire beam, but I don't want it through the entire beam. I only want it over half the beam. Well, the way I can do that is I can cancel it out by starting at that halfway point and adding an equal and opposite distributed load. So those two distributed loads will in essence cancel each other out. So and this would also, that blue would also be that same 3 kilonewtons per meter. So now I'm going to have a plus going in the opposite direction, that 3 kilonewtons per meter, and that is starting at x equals 5 meters. So I have x minus 5, and this is to the power of 0. Now I'm getting a little loosey-goosey with my units. It doesn't really matter. As long as I am at the very end, I realize what units I'm in. If you want to see the notes with the included units, you can go to Blackboard. So once again, what I did here is I turned off the distributed load, and that happened at x equal 5 feet. Now the last one is our other point load over here, our other reaction of 3.75 kilonewtons. It's pointing up. So I'm going just like the very first one. This is case number 2. I'm going to use this equation where x is at the end of the beam at 10 feet. So, or sorry, 10 meters. So the last step would be plus that 3.75 x minus 10 and all of that will be to the -1 power. So I'm getting all of this right from, there's my -1, just copying that whole thing down, right? But here's the cool thing about these singularity functions, is we said that that I can look at when this will be on versus off. When will I count that part of the singularity function? And when x is, or when a is less than 10, it won't be on, right? Because I can't have, actually I should say x is less than 10. It won't be on, because I would have, say at x equal 5, I'd have 5 minus 10, which is -5. I can't have a negative in the brackets. So the only time it'll ever be on is when I get all the way to the end of the beam at 10 meters. Well, 10 minus 10 is 0. So this whole last term will always be equal to 0, because our x value will always be less than or equal to 10. Now this is always true on the end of the beam. So you can use this fact and just ignore the last load, point load or distributed load, like turning it on or off or whatever, at the very end of the beam. And because that's true, what I typically do is I don't even draw that in there. You know, there's no reason to add that extra term. It's just extra writing. So that was step 2. After step 2, we said step 3 is to integrate. So our first integration from our load would be our shear force. Now make sure it's a capital V, not our deflection. That's equal to the integral of our load. And now I'm just going term by term. I forgot my little dx in here. Dx. Now I go term by term, and starting with that 11.25, the way I integrate it, because it's a -1, I'm not dividing by anything. I just leave this term the same. Now here's another little thing. Because this is x minus 0, 0 isn't really doing anything, so I'm just going to put in the x like that. And this is to the 0 power, because I integrated, raising my exponent up by 1. So two things I did there. One, I dropped the 0 because there's no need. You could have done that in the load. I just was showing you how it matches up with the table. But let's keep going. So I have minus 3x, and then I'm also dropping that piece, and then 0 plus 1 is to the 1 power. And then the last one I have plus 3, and this is at x minus 5. And that is also to the first power. And I'm just dropping that last term, that 3.75, because it doesn't have anything to do with anything. So that's my first integration. Now my second integration is the moment. So this, of course, is the integral of my shear equation that I just came up with. So integrating that, I have 11.25 x to the first power minus, now I am in the positive realm for my exponent, so this would be minus 3/2 x squared, and then plus, to turn it back off, 3/2 x minus 5 squared. Now, this is where I was saying if I wanted to, I could have started here. And the way I do that is I go back to this. I have my original loading function, right? Or my original loading. And instead of using the loading function column, I can use the moment column. So if I have a reaction on the end, case 2, it says I use this equation, the magnitude of the reaction, x minus a to the first, and I should see that right there. So there's my load on the end, x minus 0 to the first power. So that's why we say we could start there, and I will, usually start right there to cut off those first two integrations. Now the other thing here is we need to add in this EI, this constant EI, because we're saying that we have our moment curvature function. So I always add it right at my next integration. So I'm going to say this next integration is EI theta of x. So as a reminder, just don't forget to add that EI once you get to this point. So continuing on with my integration, well, first let me say that what integration it is. It's equal to the integral of the moment. Continuing with this integration, now I have 11.25 over 2 x to the second power minus 3 over 6 x cubed. Now notice, I know that this is a half, but I leave it as 3 over 6. That way it's easier for me to track my numbers if there's a mistake somewhere. So I'll do that whenever I'm doing these integrations. Cubed. Now at this point, is where I start getting these constants of integration. So I just integrated for a moment, and this is where I introduce my first C1, my first constant of integration. If you're wondering why we don't have constants of integration on our two first integrations, it's just because it's almost like a rule of statics. If you ever did shear and moment equations based on the load, when you integrate, your constants of integrations are actually the load at the end and the moment at the end. Our moment at the end is 0, by the way. So it's already been included. We don't have to worry about a constant of integration for those first two steps. This is where I get my first constant of integration. So integrating one more time to finally get to our deflection as a function of x. I know that has to be the integral of my theta of x. So now I have this 11.25 over 6 x cubed minus 3 over 24 x to the fourth plus this 3 over 24 x minus 5 to the fourth plus c1x plus c2, something like that. So that's the integration. We said step 5 is to get rid of those constants of integration by using our, step 4. Get rid of our constants of integration by using these either initial conditions or, I was brought up teaching or taught that they were boundary conditions. All it means is what I need to do is to get rid of these C1 and C2, I have to figure out where I know something about the slope and that deflection. So if I come up to here, I don't really know much about the slope. I do know the deflected shape. If I had to draw it or sketch it, it would be something like that, right? Very exaggerated. But I know what my V value is. That deflection is going to be 0 at point A because it's a support, and 0 at point B. So those are my two initial conditions or boundary conditions that I'm going to use. So the first one says at x equals 0, I know my deflection is equal to 0. So I go back into my deflection equation, this last thing we have here, and I have EI times 0 is equal to, and then I just put in my 0 for x. So I have 0 cubed times all that, so that's equal to 0. And then this term would be 0 to the fourth times negative 3/24, so that's also 0. Now be careful with this term. What is 0 minus 5 to the fourth power times 3 over 24? It's 0 because it is off, right? So this is 0 because we have our x less than 5 meters, so we can't have a negative in there. Keep that part straight. Don't forget how these singularity functions work. Plus C1 times 0 is 0. Plus C2. So clearly that means our C2 is equal to 0. Not too bad. Now the other boundary condition or initial condition that I know is at x equal 10 meters, my deflection will be equal to 0. So it starts off almost the exact same. I have the total deflection is 0, so EI times 0 is 0, is equal to, let me get rid of all these things, right? The first term, I'm just putting in these values, so I have 11.25 over 6, and I'm going to put them as parentheses now because now I can't actually multiply it. They aren't singularity functions. But I have 10 cubed minus 3/24, 10 to the fourth plus 3/24. Then I have this 10 minus 5, so I have 5 to the fourth plus C1x, which C1 is my unknown that I'm trying to solve for. X is 10, and then C2 is 0. We've already solved for that. So from here, I can solve for C1. If I did all this correctly, I'd find out that C1 is equal to negative 70.3125. If you're curious about units, what we're at is kilonewton meters squared. I'm not particular about units on this. I think that the key is to develop these equations and then keep your units in the original form, and either adjust your EI or adjust it at the very end. I'll explain that more later. But here's our final solution then. Our deflection as a function of x is equal to, now I'm moving the 1 over EI to the other side to make my deflection all on one side, if that makes sense, is equal to we have 11.25 over 6. I know it's weird to have fractions and decimals. If you look at my solution, I actually put it all in decimal form. You can do that if you want. And what do I have here? X cubed minus 3 over 24 x to the fourth. Notice I'm still in singularity function because when I want to know the actual deflection, I'm going to go back, and it depends if the deflection, if I'm looking at it, is if the singularity function is on or off. I have x minus 5 to the fourth power, a little better, and then I have this constant minus 70.3125 x. So that's really what I'd be interested in. I'll just quickly show the theta. I won't go through it in too much detail, but I'll just bam, and there it is. And that would do it for my deflection, and also for the, oh, that didn't do it, a little formatting issue, for the deflection and also for the rotation. And the way these work then is if I wanted to know what is my deflection at x equal 2 meters or something, right? I just plug in 2, and this would be 0, this wouldn't be on, right? Plug in 2, 2, and then whatever answer I get is what I have. But being careful of units, what I would say is if I'm going to do 2 meters, I would have to make sure my E value and my I value are in units of meters, which is a little bit funky, but what are you going to do? You could also start this original problem and convert everything to newtons and millimeters if you didn't want to worry about that at the end. So let me do one more example. I'm going to do the next example as a separate video since I don't want these to be too long, and I'll talk to you all later. See ya.